lot of people have contributed to various parts of this talk. For a lot of the decadal variability part, and IPO, Hyen, who's here, Aishu Hu, and Julie Arblaster. For the pacemaker runs, we've had a number of people working on this, Nan Rosenblum, Susan Bates, Clara Deser from NCAR, Ting Ting Fan, who's now back in China, who's working with Clara, and Nicola Mayers contributed to the volcano parts of this work, and there's some additional pacemaker runs that have been run by Nadia Herger from ETH, Ben Sanderson, NCAR, and Reto Canuti at ETH. So we've been talking a lot about the IPO and why we think there may be something going on in the Pacific. One way or another, it seems to be happening. We think it's internally generated because when you look at unforced control runs from a number of different models, the first EUF of low-pass filter C-surface temperatures comes out looking like this. It looks a lot like this pattern, which is the second EUF of low-pass filtered observations, low-pass filtered SSTs from observations. So that suggests that at least some of this is probably internally generated in some way. When you look at the PC time series of this, what we think is the IPO, you see this kind of big hiatus where we had a negative phase of the IPO that Shangping was just talking about. Went positive for this accelerated warming from the 70s to the 90s, and then it seems to have gone back negative. So one of the issues with sampling that we've been talking about is for our hindcast, starting in 1960, we really have this one transition from negative to positive and another transition from positive to negative. So we got a serious sampling problem when we try to interpret what's going on. But if this is internally generated, you'd expect that in even uninitialized model simulations, if by chance the internally generated variability of the IPO happened to match that of what was actually observed, you should get some agreement in at least some of the uninitialized simulations. And indeed, that's what happens. If you look at 262 possible CMIP5 uninitialized simulations, you get 10 members that actually get a hiatus as observed in the same time period, and those 10, if you composite them, have a negative phase of the IPOs. Then this again is suggesting that the IPO is important for this kind of internally generated variability, but this is not very satisfactory. In fact, if you look at some of these internally generated hiatus periods, there's one in one of the GFTL model simulations that's actually 19 years long. So you can get quite long hiatus periods just from internally generated variability in the model. But this, of course, doesn't give you any predictive information. What you want to do is try to predict it, right? And this is why, one of the reasons why we're here. But we have this kind of sampling issue. So we have a negative to positive, positive to negative in a kind of idealized way. If you are doing initialized hindcasts, you can imagine several outcomes could happen. Say you initialize the model during the negative phase of the IPO and happens to go towards positive, or vice versa. You could say, well, the model is just trying to go back to climatology. If the climatology is somewhere here in the middle and you happen to initialize in this anomalously cool phase, it'll go back to climatology, and that would give you actually the appearance of skill, when in fact model climatology by itself would give you skill. So that's not telling you a whole lot. So that's one possibility of interpreting these kinds of things. Another possibility is you initialize these heat content anomalies in these anomalous states, and maybe the model would just persist these heat content anomalies, which would give you the appearance of actually no skill at all, because you'd just be persisting the heat content anomalies and you wouldn't get any evolution at all. Or you may actually get some skill. The model may actually be trying to produce the right answer for the right reasons. And so those are kind of the challenges I think we face when we look at how we verify skill in these hindcasts. So let's just look at one way of looking at skill for these two big shifts. This is the top one here is the kind of mid-70s shift. This is a way of looking at this by taking the 3 to 7 year prediction minus the previous 15 years. So the question we ask is, how are conditions 3 to 7 years from now different from what we've just been experiencing in the previous 15 years? So this is an observationally based thing. You can see it's for the big shift, the mid-70s shift going into the rapid warming in the latter part of the 20th century. You see this positive phase of the IPO with somewhat warmer tropical Pacific sea surface temperatures. Persistence doesn't give you anything that looks like this. The initialized hindcasts from the 15 CMIP-5 models do give kind of a sense for a positive phase of the IPO, and the uninitialized really don't give you any of that pattern either. The other big shift we're talking about is this shift from the positive to the negative phase of the IPO. This is now looking at the initial year of 1996. We're looking at the 3 to 7 year prediction averaged over 1998 to 2002 minus the previous 15 years before the initial year of 1996. The observations see this big negative phase of the IPO. Model simulation really captures the kind of southwestern and northwestern subtropical Pacific part of this, gets some of the cooling in the eastern tropical Pacific, and of course that beats persistence and the uninitialized. So there are indications that maybe some of these big shifts, there are some skill, but there's these plots like this that already keep showing. So this is just one example from one of Paco's papers. This is looking at skill for predictions for years 6 to 9. Red colors mean you have good skill. You always see this, all this red in the Atlantic. You see it kind of in this area of the Western Pacific, Northwestern and Southwestern subtropical Pacific, but not much in the tropical Eastern Pacific. So if we get apparent skill from these big shifts, why can't we see it in these kinds of plots? One reason could be Mount Pinatubo. And this was a plot that we showed without the volcano stuff superimposed on it in our 2014 paper, where we were just looking, and this plot's just for the Pacific sector, and we're doing anomaly pattern correlations for the hindcast from the 15 CMIP-5 models. So high numbers here mean good skill for the IPO pattern. The red line here is the ensemble average of the multi-model ensemble average. The blue dashed line is persistence. This dashed line here is some measure of significance at the 5% level. So going across this transition from negative to positive IPO, we see we get pretty high correlations. That's consistent with what we saw in that previous plot. So we're getting this transition from negative to positive IPO. We come along here from going from the positive to negative IPO, and we get pretty high pattern correlations, which is considered consistent with that pattern, that nice correspondence we saw in that pattern. But then we get this big hole of skill in the 90s, where skill drops for at least this pattern in the Pacific sector, even to negative values. Well, that's suspiciously coincident with the time period affected by the Mount Pinatubo eruption. So Mount Pinatubo erupted in 1991. The first year after the eruption was 92. The third year after the eruption was 94. So if you look at Pinatubo affected years that go into these 3 to 7 year predictions, the first set that would be affected would be 1998 to 1992, because that'd be the first year after the eruption. And the last would be the year of 1994 going to 1998, that 3 to 7 year period. So the way this is plotted, these central years of these 7 year predictions are plotted here, and that's exactly the time period where we see this huge loss of skill. So how could this be happening? Well, one way of thinking about this is maybe the models are trying to produce a response to the Mount Pinatubo eruption that we didn't see in the observations. So these are some results from Nicola Mayer in her paper with Matt that's under review in GRL. These are observations from the Mount Pinatubo eruption here on this side. This is the eruption peak. So this is now surface temperature anomalies in relation to the previous 5 year period. There's this kind of big kind of El Nino event right at the eruption peak. Right after the eruption, the year after the eruption, this goes to a kind of a weak La Nina that still has some warming around it. Significantly, third year after the eruption, you see another big warming that occurred.
Are those annual averages?
Yeah, annual averages. Now, if you look at the model responses, what Nicola did is she looked at the CMIP-5 models. She did a multi-model, multi-ensemble, multi-volcano average. So this is kind of the canonical response that the models would be trying to produce to a given volcanic eruption. At the peak of the eruption, there's cooling almost everywhere in the tropics and subtropics, but a little bit of a lack of cooling in the equatorial Pacific. Right after the eruption, you see even more cooling, but even not as much cooling at all, and even a slight warming. These are sea surface height anomalies over here on this side, which are kind of wind force that gives you an idea of that this is really trying to produce kind of a weak El Nino-like response. And then the third year after the eruption, you get this cooling, which is kind of a La Nina-like response. So you can see just right away by eye, these aren't going to match because this is going to be a slight cooling, this is going to be a slight warming. This is a big warming, this is a big cooling. So the model responses are trying to give you something in that the observations aren't giving. So when you're verifying against observations, obviously you're going to have terrible skill for the patterns of SSTs that are being produced in the Pacific. So that could actually be one of the reasons why we see that kind of big hole in skill for the Pacific.
The observations are just kind of one ensemble.
That's right, it's one ensemble member. And this is the thing, we don't quite know. If you look at other volcanic eruptions in the same way, like Agung in 64 and El Chichon in 62, both of them had a kind of an El Nino coincident with the observation, or coincident with the eruption. They kind of had a weak La Nina that kind of got cooler, kind of weak La Nina 3 years afterwards, which actually does have better correspondence with what the models are trying to produce. So that may be one reason why they didn't have as big an impact on really affecting the skill as Pinatubo did. Okay, well maybe you don't want to think about verifying against observations. Let's think of doing it another way. Let's think about using EOFs. And so the idea here is, in this paper we had in 2014, was let's just take the 3 to 7 year predictions, the 5-year averages, and make a time series of those and do an EOF, and this is for precipitation. And so this is the first EOF, the 3 to 7 year predictions. So the sign of this would be the sign of a positive phase of the IPO, which is kind of represented here. So when you have a positive phase of the IPO, you get enhanced precipitation over the warmer water, decreased precipitation around it in Australia, enhanced precipitation over the southern interior states in the US, and this is for northern winter. And you can see some elements of that in the observations when you regress the IPO index on observed precipitation. But the point here is when you look at the PC time series from these EOFs, you get positive values here, which are consistent with the positive phase of the IPO or the positive phase of this pattern. And if you would have expected skillful predictions, these positive values should have continued on here until it transitioned to the negative phase of the IPO, which then is picked up here. But there's this drop of skill where nothing really happens here, and these are the 2 time periods that were affected by the El Chichon and Pinatubo eruptions. So we already saw how the actual pattern of sea surface temperatures could be affected by the actual observed response to Pinatubo, which may not match what the models are trying to do. And this bigger scale pattern actually could have been affected by Chichon as well. So we got this problem with volcanoes. Okay, the mechanisms, a little bit about mechanisms. There's a possibility that maybe the whole IPO thing is being forced from the Atlantic, but there's also evidence that there could be mechanisms within the Pacific that could produce this kind of decadal timescale variability. I think the first person that came up with this possibility was a paper by Warren White in the early 2000s. There's been a number of others from the Australian group and from our group. This is a representation of the mechanism we diagnosed from one of the earlier versions of the model. The idea is that when you have a negative phase of the IPO, you get negative convective heating anomalies. Anomalous Rossby wave response produces anomalous highs in the North and South Pacific, which produces anomalous winds. And in the areas, say 25 north and south, these would produce anomalous upwelling Rossby waves. Because they're so far from the equator, they would just chug across the Pacific very slowly, so that when you have a negative phase of the IPO, these downwelling Rossby waves that were initiated in the previous positive phase are finally getting over here to the Western Pacific. And when they would get here, you would expect to see a buildup of ocean heat content in these off-equatorial areas in the North and South subtropical Pacific, which then possibly could, if you had an El Nino event, could trigger a transition of the thermocline depth through Kelvin waves coming across here that would then produce a transition from negative to positive phase. So do we see anything like that in the Pacific? This is just a time series of off-equatorial heat content in the initial states that we're using to initialize the CCSM4. So what you're seeing here is these are for the off-equatorial boxes, and the boxes here are defined here in the Western Pacific. So you see relatively high values here. There's the 86, 87 El Nino event, and then they start dropping. They drop until we get the big, actually the key thing for this transition is the 2-year La Nina event from 1990 to 2000, and then we start seeing this increase. So the suggestion here could be that you need this kind of heat content buildup from forcing from tropical mid-latitude interaction with these ocean Rossby waves that can then be triggered, transitions could be triggered by interannual events. Do we see anything like this? Kind of. This is now looking at the CCSM4. This is Nino 3.4 predictions for initial years of 1976. Observations are black. The ensemble average is red. You can see that the model does capture a little bit of this 76, 77 El Nino. The model actually stays relatively warm. That's associated with that transition to the positive phase of the IPO for the early 2000s hiatus. On the ensemble average, it does get a weak version of this 97, 80 El Nino, but more significantly, it gets the 2-year La Nina afterwards. It stays relatively cool. So there may be something going on that could produce this kind of timescale interaction. If you look at predictions now for the next time period, initialized in 2013, haven't updated the observations here yet, but basically we saw this kind of measly El Nino in 2014, where it's a little bit bigger in 2015. This indicates that we'd see a transition over the 2015 to 2019 period to a positive phase of the IPO and a resumption of warming. So that's an application of that idea. But maybe we're just barking up the wrong tree here. Maybe everything's coming out of the tropical Atlantic, which would be great, because then you don't have to predict one thing. If we could get the tropical Atlantic right, everything else would just fall into place. So is that a possibility? So this is, of course, Shangping's pacemaker runs. These are the ones we've been doing. We've done a set for the Pacific, try to reproduce what Shangping did, and a set for the Atlantic. So we're just restoring the MO region from equator to 60 north with observed SSTs, not the MO pattern, just observed SSTs. This is the globally averaged temperature time series. This light green line here is from the Atlantic pacemaker runs. The red line is the ensemble average of 10 ensemble members from the Pacific pacemaker runs. You can see that we're not quite done with the Atlantic pacemaker runs yet. Looks like they're continuing to go up. The Pacific pacemaker runs agree with the observations somewhat. We're getting a little bit less agreement right at the end there. We're doing some runs now to put in the early 2000s volcanoes to see what role they have. As Shangping pointed out, we see this really nice agreement, which indicates the IPO was really contributing to this early century warming that the Atlantic probably wasn't doing a whole lot with. But there's some interesting aspects there. But the question we wanted to ask with these is the Atlantic driving the Pacific, or is the Pacific driving the Atlantic? So just taking Shangping's simulations and just doing lag correlations with on the decadal timescale of 10-year running means. This black line is the average of his 10 members, and you can see that it's peaking here with the Pacific defined as that, the IPO defined as that just box in the Eastern Pacific. The tropical Eastern Pacific's leading the AMO, but you can see there's a lot of variability across the ensemble members. This ensemble member has the Atlantic leading the Pacific, so there's a lot of variation across the ensemble members. If you look at our simulations, let's just look at the annual mean values first. The green line here you can see has this really nice indication that the Atlantic is leading the Pacific by about 2 or 3 years, and I think that's consistent with what other people have been showing. But if you look at the Pacific part of it, you see the Pacific seems to be leading the Atlantic, at least in some way, and neither one of them seem to get this observed 1-year lead of the the Pacific leading the Atlantic. Looking at the decadal timescales and doing these lag correlations, the observations seem to suggest this kind of weak tendency for the Pacific to lead the Atlantic. The Pacific pacemaker runs seem to get some of that, and the Atlantic pacemaker runs, even though there's this little bump here, aren't as strong. So I would say that this is equivocal. This is our restoring. We're using a 2-day restoring over the first 10-meter model layer. So that's another little bit of a difference from some of the other things. The last thing I wanted to show were some kind of sensitivity experiments that were done by Nadia Herger, Ben Sanderson, and Reto Canuti. They were just adding 2 degrees to 3 different bands of the Atlantic. So this is a pretty big hit on the system, but they were trying to give it a really hard hit. Their actual goal was to see if they could kill El Nino, what it would take to kill El Nino from the Atlantic. But they've got a lot of other interesting results here. The first thing, of course, is that as has been shown a number of times, the tropical Atlantic one gives this nice response that looks like the IPO in the Pacific. So I think that's consistent, even though with this somewhat different methodology. What I thought was interesting was this time series of Nino 3.4 over the duration of these experiments. And the key for these, the control run, is the black line. So you can see these are the El Nino and La Nina events going on in the control run. Using the whole North Atlantic, the blue line here, you can see that the amplitude has really been reduced. Equator to 20 north also reduced quite a bit. It's only when you get to the 50 to 90 degree north where you get something that's close to what was in the control run and even somewhat bigger amplitude. So the effects on interannual variability, and I think this was kind of consistent with what was shown earlier as well, there's interesting effects coming from the Atlantic on the nature of interannual variability in the Pacific. So the questions for us, do these pacemaker runs teach us anything about the system? Clara Desser, one of her main points was that even in the Pacific pacemaker runs, you still get model systematic errors that kind of cause complications, especially if you're looking at precipitation anomalies and teleconnections. It seems like, looking at these Atlantic and Pacific runs, that if you specify part of the system, the other system is going to respond to it kind of no matter what. So if you specify the Pacific, the Atlantic's going to respond. You specify the Atlantic, the Pacific's going to respond. So it may not give us a very good idea of how coupled interactions work for that problem. It looks like from these runs that sometimes the Pacific forces the Atlantic, sometimes vice versa, but there could be timescale differences. So there could be different things going on the interannual timescale versus the decadal timescale. And then the question we have to ask is this really justified? Can we justify a large effort by the community with coordinated multi-model set of pacemaker experiments in terms of defined science questions or questions that pacemaker experiments can answer? So just to summarize, I think it's pretty clear now the IPO is internally generated, at least in these long model control runs. Some of these uninitialized CMIP5 simulations get the observed hiatus negative IPO if their internal variability happens to match what happened in the observations. But we're interested in predicting this thing, so there does seem to be some skill in predicting the IPO and the initialized hindcast, but Mount Pinatubo seems to be a real factor in affecting how we assess skill in the Pacific during the 90s. The mechanism possibly could be within the Pacific with this kind of slow motion delayed action oscillator mechanism, but maybe the Atlantic could be forcing the IPO in the Pacific. I would say so far the evidence is equivocal. It seems like the Pacific sometimes forces the Atlantic, sometimes vice versa, and there could be timescale differences. Thanks.
You went through it kind of quick. I was wondering, you mentioned the 3 volcanic eruptions, Aspen, Ocillation, and Pinatubo. You said that there was a difference in the response between Pinatubo and the other 2.
Yeah.
By the way, Aspen was in 63, not 64, so I wonder if that was a typo in your...
That was a typo in my, yeah.
But you did use the right years.
Yeah. Yeah, so yeah, I think when you look at, especially the 3rd year afterwards, you know, there was a big positive anomaly there, and the 3rd year after in these 2, there was both negative, and this actually was more consistent with, or would be more consistent with the models we'd be trying to predict. So I think that's why, that's one of the big differences between, you know, Pinatubo being really at odds with what the models would be trying to produce. There was this big warming for whatever reason, and then the models would be trying to respond in another way. So we had this big debate, you know, and you raised this yesterday and everybody just started grimacing. We had this, it's an ongoing thing. It's lasted for, I don't know, 7 years we've been arguing about this. Whether you include volcanic eruptions in the hindcast or not. And the argument for including them is the verification data has the effect of the volcanoes in it. But you may be introducing artificial skill by the volcanoes giving you a force response you wouldn't know about in advance if you're doing a prediction. But I would say that, and I think Doug tried a calculation where they had the no volcanoes versus volcanoes, and he decided it was a 5% effect, plus or minus, but it may be dependent on the volcano. And when you're looking at it.
Huge El Nino for Ocillation that started before the eruption.
Yeah, this one.
That's Pinatubo,
Or,
but it was much bigger for Ocillation.
yeah, this one.
Some people try to tie that as
Yeah.
being caused by the volcano, but
Right.
Nicola's results show that that El Nino response is like in the next year, not simultaneously. So unfortunately, I don't have enough eruptions.
Yeah,
to
sampling is a problem.
Sort of on that point, Jerry, as Matt knows, Ben Santer and I were looking independently at this particular problem and have sort of twisted ourselves in knots trying to see this in observations across all three of these. But you get a lot of useful information from large initial condition ensembles. So we have a 100-member large initial condition ensemble with natural forcing alone. And it's clear there that you need a large number of members in order to see this effect due to the compounding influence of ENSO. This is what, this is exactly what.
Yeah, so this is, I didn't say that this blue line here is the large ensemble with CESM 1, which should, in theory, give you at least some kind of forced response. And you can see, actually in all of them, you see these volcanic eruptions. But then there's this thing about, this volcanic forcing data set may actually be giving you too strong a response. So we've rerun the more recent period with this a version of the new Vernier data set, and this kind of overreaction to Mount Pinatubo seems to be not as big using this new volcanic forcing data set.
Is that data set been published? I'd like to compare that to like the older ones that... I'm not the person to ask, but as far as I know, the Vernier, and somebody else may know this, Vernier, I think, published something, right? And then Ryan Neely took a version of that, and that's the one we've got. We've done these just sensitivity experiments so far, and these are the ones Ben has been trying to analyze for the early 2000s volcanoes. But as you know, That's more recently. Does that go back all the way to?
It goes back, I think, to Ryan, to 1940, 60. It doesn't go all the way back to 1900.
CCMI data set, which has been compiled for the CCMI. So it's by the Swiss group ETH and then Vernier, Thomason, and this guys. So based on SAGE and then on Calypso for the later period.
So does it go back? How far does it go back?
From 1960 to
60.
Yes, this is for the chemist.
Right.
It was developed for the CCMI initiative.
Right. I think that's the length of these additional runs we did at the volcano only forcing.
So Jerry, on your conclusion that these shifts are highly predictable, so if I understand it correctly, what you've done there is taken away the observed pattern immediately prior to the shift and put that in your forecast. So what you've effectively done is kind of flipped the opposite phase of the PDO, put that in your forecast. So even if there's no skin in your model projections, that has the kind of impact of kind of giving apparent.
That's right. And this is why I was making this point. You can get apparent skill just from the way you set it up, or if your model is just trying to go back to climatology. And I think we had this email exchange that climatology gives you really great skill because if you're initializing in some anomalous state and it goes back. I actually asked Mark Kane this question at the Kane Symposium. I said, well, you guys must have had this same issue in the early days of ENSO prediction, because you must have worried that if you're in a La Nina event and you initialize in the La Nina and the model just wants to go back to climatology, it's going to look like we're going into an El Nino. And he said, oh yeah. He said, we worried about that a lot. And he says, but we had just a lot of samples, so we could just beat it back with a lot of samples from the observations and then make these long model runs. I still think we can do a lot more on these, hearing these talks. I think looking at these long unforced control runs, we can do more analysis on those to get more samples. Of course, we won't have volcanoes in them, but you could look at these connections between Atlantic and Pacific. It's model dependent, so you probably have to look at a number of different models, but I think looking at long control runs may give us more of an idea, because I think this is an issue we got. We don't have many samples, and the way we're verifying, that's why we went to that EOF-based kind of system where there weren't observations involved. You were just looking at where'd it go? Yeah. So I mean, these are just EOFs of the 3 to 7 year predictions, so there's no observations in this. And this is just showing that, yeah, you do get this positive phase of the IPO. You lose that pattern for a while here, maybe because of the volcanoes, and then you get it back here in this kind of negative phase. So that's another way of at least giving you some idea that maybe the model is doing something that's right.
Just another comment on that is that you can compare against a damped persistence as opposed to a persistent. And that actually will guard against attributing scales to the climate level.
Yeah, because the persistence we were comparing again was just straight,
Yes.
take the previous 5 years and just say that you just
Right,
keep
but if you just
persist that.
if you just compare it against the scale not from persistence, from damp persistence,
Yeah,
you can at least see if you're beating that.
right.
No?
Yeah, I'm just curious about this. I think you're making the case that when El Nino goes off during the forecast, right, then it will screw up the verification.
No, volcano.
Yeah, okay, but I mean, if those particular El Ninos were internal dynamics,
Yeah.
so is it that what you're saying, or is it that the volcanic effect is so strong that it always produces, then you have this much bigger RMS difference in that case?
My interpretation is that the model response to these volcanoes is stronger than what the model would be trying to produce from internal variability. That's the interpretation. That may not be right. And there's questions about the system responding, how the system responds to volcanoes. It may be dependent on the initial state, and I think this VolMIP, I think, is addressing that. So if a volcano goes off during an El Nino event, you may have how it plays out over the next 3 years may be different than if it goes off during neutral or negative.
The phase of the QBO when it goes.
QBO, yeah, so there's all these,
Probably don't have.
volcanoes are a real nuisance, you know, if we just
Yeah, that's good.
make them stop happening, you know, make our
I like
life
to
easier.
say more of them myself.
But what's really nice is a really nice nature experiment.
Yes.
Yeah.
That's really the great thing on it.
And we're due for another big Pinatubo style eruption, right?
Yeah, definitely.
Is that a prediction?
This is what
Yeah,
they
it's
said.
going to be in the spring in Indonesia.
Okay, so we'll take Crystal's comment and can we set up for the next talk?
So just one comment on your implied relationship between AMD and I've done some calculation from the simplified industrial control simulation. So taking the 1,000 years that you get from this data set, and what I found is that the relationship actually is not stationary. I mean, you can find periods of different century where the AMO is leading the APT, and the next century it's opposite in the same model. So I think it's going to be very complicated to reach a consensus or a result on this.
Yeah, this is when we were looking at this, 10 years ago, trying to look at the mechanisms. Each of these decadal seems to be different.
Yes.
In the Pacific, almost like each El Nino is different.
But that one.
And so sometimes you get a big contribution from the North Pacific and none from the South Pacific. Sometimes you get more from the South Pacific. And so then you've got that, and then you've got, and that may play into how the connections go across the basin.
Yeah.
So it may be episodic.